Record. Okay, so this is technically the last tutorial, but I think Jan probably told you that he's a bit ahead on schedule. So the next lecture, he'll take you through tutorial 10. So you'll get to see all of the questions. Okay, but for now, we'll just do tutorial 9 and it should be fairly easy to fit in. Okay, so for this one, we have more inflation stuff. So imagine a scalar field with this kind of potential, and the little m represents some mass scale. Doesn't really have to have any physical significance. For part A, compute a potential slow roll parameter for this potential and try to identify the region where slow roll inflation may be possible. So the potential slow roll parameters are just the epsilon v and eta v. Give me some space. Okay, so epsilon v, that's mpl squared divided by 2 v dash on v squared. And then eta v, that's the Planck mass squared second derivative on v. Okay, now we're just given the v, so all we have to do is just work out these two derivatives. So v prime is minus m to the 5 on phi squared, and v double prime is 2m to the 5 on phi cubed. Okay, so then putting them in, epsilon v would just be mpl squared on 2 m to the 10 on 4 phi squared divided by m to the 10. So all the masses cancel out. So you just end up with phi squared. Okay, and similarly for eta v, do the same substitution, but it's just for v double dash and then on the phi squared phi divided by m to the 5. And you end up with 2 mpl squared on phi squared. Pretty much the same, except slightly different constants. And the slow roll condition is basically the same as well. So you just require epsilon v to be much less than 1, and also eta v, the absolute value, to be much less than 1. And these two are going to give pretty much the same limits. They're just slightly different. So if you take the epsilon v one, epsilon v being very much less than 1. I don't know why I wrote that down again. So that would just be mpl squared on 2 phi squared much less than 1. So phi will be, absolute value of phi will be much less than mpl on root 2. And similarly for the eta one, you'll get just the same thing, but the 2 in a different place. So then phi is much less than root 2 mpl. And this is a slightly stronger condition. So this is included in that, in this range. So you can kind of ignore or just assume this one's already like kind of included here. So you can just take this as the condition and it's fine. And okay, so absolute value of phi less than this amount, and phi clearly takes like a what's it called, hyperbola. So in your phi v phi space, it will look something like this, your potential. So then at some point, so here where we have root 2 mpl, then if you're towards the right of that, then it's fine. So slow roll is allowed, or like slow roll condition met. Similarly for this side, if you have minus root 2 mpl and you further to that side, then also slow roll conditions met. And that kind of just visually looks correct as well. If you're here, then you'll be rolling down the hill very relatively quickly. But then by the time you get to here, then it'll be a very slow rolling from that point onwards. So yeah, the two tail regions of this potential can support slow roll inflation? Inflation. Yep, here we go. All right. Okay, part B, using the slow roll approximation, estimate how many e-foldings the scale factor increases as the field rolls from 10 Planck mass to 20 Planck mass. Okay, so here's like, there's lowercase m, but it's just the same thing as uppercase. Just, I don't know why the notation is a little bit different. But okay, so you basically just using the slow roll approximation, so that tells you that epsilon v is approximately equal to epsilon h. So that will come in handy when filling through the algebra. But you just start with the number of e-folding definition. So that's integrating from the starting time to the ending time. How many Hubble radiuses you've managed to cover, or like how does the Hubble evolve in that time? Okay, and to do this, we have the potential and the slow roll parameters for epsilon v, which is all function of phi. So here, you don't want to work in time. So you want to obviously just change a variable to the phi variable. So go to phi 0, phi 1, h, dt, d phi, d phi. Okay, and then using Friedman, if you combine the two Friedman equations, you should find the h dot is equal to minus 4 pi g phi dot squared. So here, this is 1 over phi dot. So you can use this to substitute this out. Then this gives you integral from phi naught phi 1 square root of 4 pi g. It's a 1 on? No, it's square root of 4 pi g. And you have h on square root of minus h dot d phi. This looks a bit weird, but don't worry, because when we use the epsilon h definition, this thing is minus h dot on h squared. So this you can sub out as a square root of epsilon h and not have to deal with anything that's actually imaginary. So yeah, swapping those out, so we get root 4 pi g integral phi naught to phi 1, 1 over square root of epsilon h d phi. And now we use the slow roll approximation to sub out the epsilon h for epsilon v. And that gives us, okay, approximately. Okay, and now we just have to substitute in this definition of epsilon v. And we already know what this, so we can just pretty much sub this thing in. And you have 4 pi g's here, and in the definition above, you have the Planck mass. So just make things neater, just sub in Planck mass is 1 over 8 pi g. So pretty much after doing some algebra to just shoving everything inside, you get 1 over Planck mass squared, integral from phi naught to phi 1 of phi d phi. Okay, and now that, yeah, we know the limits of this integration, so it's just fairly simple. So it's just going to be PL all squared minus 10 MPL squared divided by 2 MPL squared. All the Planck masses cancel out, so the numbers after working out, it just works out to be 150. I can't remember on top of my head, but I feel like that, I think that's like a lot. I think for our universe, you only need like 60 e-folds to explain the coincidence problem. So this is already like a fairly exaggerated amount of inflation that's happening. Okay, so for C, is this a realistic model of inflation? You don't even, okay, this might be a good indication, but like you don't need to actually refer to this. The main problem with this model being not realistic is the hyperbolic functional form of it, because it just keeps going. So you can see that as the thing keeps rolling, slow roll condition always holds. like as t goes to infinity. So as time goes on, the slower condition keeps holding. So then your universe just keeps inflating. So inflation never actually ends. And yeah, so that's first of all a problem because we know inflation has to end at some point. Otherwise, nothing will ever happen in this universe. And also another point is that this potential doesn't have a vacuum. Or like another like more simple way of saying it is it has no minimum. So it kind of asymptotically approaches a flat solution at infinity, but then it doesn't actually have a real minimum. And that's a problem because then reheating can never happen. Which kind of is like a secondary concern, because if inflation never ends, then like it doesn't really matter if nothing happens anyway. But yeah, so the other related parallel problem is that during inflation, there's no standard model particles. You have to create standard model particles at the end of inflation when the inflaton field reaches some potential minimum, and then it starts oscillating back and forth. And this oscillation then decays into particles. So if the potential has no vacuum, then it will never reach this minimum and will never oscillate. So then you'll never actually get to create any standard model particles. So your universe will just remain empty. So it will just keep inflating and there will be nothing ever in it. So we wouldn't exist to be here to ask this question. So no, not a realistic model of inflation. But we can actually make this realistic, and it's quite an interesting exercise. So to solve both of these problems at the same time is to add a second dimension to the potential. Add another dimension. So right now we have just the phi dimension, but then now we're adding another, let's call it chi dimension. So our potential is actually now like a 2D potential. So V, let's call it V tilde of phi and chi. It's equal to the original potential that we have. So just the pure phi potential plus G squared on 2. So this is going to bring back some particle physics flashbacks. Chi squared plus 1/4 lambda squared. Okay, and then M tilde and capital M, they're also just some mass scales that you fine tune in your model. And lambda and G are just dimensionless coupling constants. Oh, they don't have to be dimensionless. I think in this case they are dimensionless, but they don't have to be. But anyway, so this is now interesting because, so if you remember from particle physics, actually, I don't know if you'd cover this in particle physics. Hopefully you cover this in particle physics. So the mass of a field is the second derivative of the potential with respect to that field. So then from this potential, we can then look for, actually, this is more of a stat mech, a solid state physics kind of thing. But anyway, so we can then ask for what the mass of this chi field is, this additional dimension that we've added in. So this chi field, if you take the second derivative of this whole thing, then you end up with G squared M tilde squared minus phi squared minus M squared. Okay, so this is pretty interesting now, because if phi is larger than M tilde, then this term is negative. Oh, sorry, this is M squared. So this term is negative. So then what that implies that at that regime, M chi is imaginary. And then when phi falls below M tilde, then M chi suddenly becomes real. So if you looked into the Higgs mechanism, then this is exactly the simple Higgs potential. So above this, your potential looks something like this. And then as you go below the mass range, then you develop something like this. Then you roll down to one of the minimas, one or the other. And so this essentially means that some kind of spontaneous symmetry breaking happens at phi equals m tilde. So this becomes very interesting for us then. So drawing the picture out, let me try draw this. So imagine this is your v tilde and this is your chi, this is your phi. If you're rolling down, so the phi part will just keep being like this hyperbola coming down. In the chi dimension, so this way, at high values of phi, you're going to end up, at high values of the field, you're going to end up with like these, what's it called? These kind of before the symmetry breaking, so you have imaginary mass chi. And then at some point, you're going to create like a double dip like this. And then the field then rolls down into one of these into one of these vacuums. So then you can oscillate inside this vacuum while still going ahead in the phi direction. So you're kind of like zigzagging along. So you're oscillating in the chi direction, but then keep traveling in the phi direction. And that's fine because the oscillation in the chi direction will eventually create reheating and also break the slow roll condition. So then you exit inflation and plus you're able to force the inflaton field to decay into standard model particles. So this is called a hybrid inflation, where you're using the phi field to drive the actual inflation. And then you use the chi field to break the inflation and then drive the reheating process. So you're combining two of the things together to make it work. Does it sound contrived? Yes, but then all inflation models are pretty contrived. It's hard to really say what is natural because we just can't see anything observationally. So basically, if you can make up any model that gives us enough e-foldings to create a sufficient amount of inflation, and then also to come out with standard model particles at the other end, it's fine. So yeah, there's a lot of fun you can do with it if you want to like build inflation models. All right, any questions about this? Oh, there is. Sounds like string theory. It pretty much is, yeah. Like a lot of these things, a lot of these are actually very closely tied to string theory. So a big problem they usually cite is that your universe goes from like the singularity to this inflation phase. So then you're going from a very high energy grand unification theory to very quickly going into some kind of weird Planck mass driven inflation period. So then logically speaking, whatever field that drives inflation should be a classical inheritance of the string theory field at the singularity. So they actually do make a point to sometimes prove that a lot of these potentials that they derive for inflation are like the classical condensation of a string theory potential. So yeah, the two are actually pretty much intimately connected. One has to lead to the other. Okay. If no problems, then we'll move on to the second part, the second question. Okay, here you have a coherent oscillation of a scalar field. So at the end of inflation, you expect the inflaton field to perform oscillations around the minimum of the potential. You can expand the potential around the minimum. So just do a Taylor expansion. Assuming the higher order terms are negligible and that the oscillation is weakly damped, find the time average equation of state parameter W for the system. Okay, so we're just taking the first order term, and yeah, the weakly damped just means that you are now out of the inflation phase. So you're no longer, your field is no longer stuck by the Hubble friction. So then it's able to actually quickly oscillate. So we always start with the Klein-Gordon equation for these. So phi plus 3h phi dot plus v dash equals 0. Okay, and since that is weakly damped, so then we can ignore the Hubble term. The Hubble friction term no longer plays a big role. So we just have these two. And v, we're just going to take this v. And the minimum is, it's technically, in general, is there, but like there's nothing really forcing you to pick any particular minimum value. So you can kind of choose whatever you want. And in this case, like at the beginning, we keep it there to show you that it's an expansion around the minimum. But then there's nothing stopping me from just calling the minimum 0. So then simplify the potential field to just half m squared phi squared, which is a lot easier to work. So then v dash is just m squared phi. So putting here, we have the Klein-Gordon equation plus m squared phi equals 0. Okay, that's a very trivial differential equation to solve. So then your phi would just be a oscillation sinusoid. So have some maximum amplitude and then cos omega t. You can there's technically a sine part as well, but then you can always adjust the phase to delete the sine part. So you can just only use the cos component. Okay, actually, yeah, this omega is kind of a notational convention to call it a frequency, but actually it's just the mass cos mt. So omega equals m. Okay, so now we want to find the equation of state. So equation of state W. Okay, that might be a reason to use m instead of omega, so we don't get confused with the W. Okay. W is equal to the kinetic energy minus the potential energy divided by the kinetic energy plus the potential energy. So this works here because the entire universe is dominated by the scalar field. And for scalar field, the pressure is T minus V and energy density is T plus V. So yeah, this works for the scalar field perfectly well. Okay, so now we just have to find these individually. So the average kinetic energy will just be average of half m phi dot squared. And putting in this solution for phi, we just get average of half phi naught m squared sine squared mt. Okay, and the half, the phi naught, and this is phi naught squared actually, sorry. And the mass, they don't vary, they're fixed values. So it doesn't really care about this averaging, so we can take it outside. And so all we have to do is just average the sine squared. And average of sine squared is always half. So you just integrate over, you just integrate sine over 2 pi on m, and then divide by the period 2 pi on m, mt. So that would just be sine squared. So that would just equal to half. So then this whole thing just equals a quarter of phi naught squared m squared. Yep, that's what I got. Okay. All right, and then for the potential energy, we'll just be taking the formula's potential and then putting this phi in there. So then we end up getting half m squared phi naught cos mt all squared. And again, the half and the m squared and phi squared comes out, phi naught squared comes out, and then cos squared mt. And cos squared mt, you do the exact same thing, and it ends up in half again. So just a quarter m squared phi naught squared. Okay, so t is obviously equal to v looking at these two results. So that means our equation of state is actually 0. So at this point, what this tells us is that this inflaton field at this point acts like pressureless gas or pressureless dust. Cool. Okay, and you can do this for this is kind of interesting to generalize to other potentials as well. So this one right now, we're assuming that V is phi squared, but then you can technically make up an inflation model where V is to phi to the n, or like proportional to phi to the n. And you can go through this step again, but then the problem is that this differential equation becomes really weird, because then you're gonna get like phi to the n minus 1 here, and you could get like Weierstrass function. Does it act like that when n and when phi min is not 0 too? Yes. Okay, I know it's yes, but hold on, let me think how does it mathematically work. If we add in the phi min, we just end up with another term in here, a constant term. And so you'll end up with just the phase shift. And then when you do the averaging, the phase will drop out. So then you end up with the same expression for T and B, I think. Yeah, physically, I know it definitely doesn't care about what phi min is. Just mathematically, I'm not 100% sure on top of my head. So if phi min is not 0, then, oh, actually, does it even survive this term? Oh, no. So then we'll have this phi minus phi min. And then when we take it here, our differential equation becomes phi double dot plus m squared phi equals m squared phi minimum. So then this looks like a oscillation with a is that a driving force? No, it's not, is it? Is anyone like recently done a differential equation course and know what this solution looks like? Oh yeah, okay, yeah, there we go. There's the answer. Oh, let's just mathematics at this. Sure. Okay, what am I solving? Desolve m times phi equals c. Yeah, it's the same. You end up with a constant term out of front, which wouldn't okay, let's push this through and see what happens. So what did I end up? So I end up with so my phi now becomes phi naught cos mt plus c on m, or c is like the phi min on some m squared probably. And then okay, and then when I take the derivative here, this will drop out. So the kinetic energy stays the same, but the potential energy means that I will have an extra bit in there. Oh yeah, that's actually dangerous. Okay, so the potential end up being half m squared phi naught cos mt plus half m squared c on m squared. So that equals m squared phi naught squared, and then average over distance. You do get a potential shift. Did I do something wrong? Let's see. Oh no, sorry, no, this is fine. I goofed this part. Okay, so yeah, it's fine. Let me try this again. So V would be half m squared phi squared. So then it will be half m squared phi naught squared cos squared mt, and then plus the cross terms between, where was it again? Between the c and the stuff. So you get like a c phi naught m cos mt. I mean, you still end up with a c squared m squared at the end. So these will drop out because the averaging over cos is 0. This term stays though. Let me think about this. I don't I don't actually know. I don't I must be doing something wrong algebraically. I don't think this should matter, but for some reason it's not leaving. Actually, maybe it's still this averaging part that start doing it. No, if I integrate this, it just pick up the t. Okay, let me think about this. Let me just go through the next part first, just so that I have covered it. So the general way to do this for a general n actually appeals to Viril theorem. So for Viril theorem, where it says that you relate your potential energy to the kinetic energy like this. So normally you might see this as T equals V, because N usually equals 2 for gravity, so it shows like this. But yeah, in general, you can get Viril theorem like this. So then using Viril theorem, then you can always, for general N, to always get the equation, say W as T minus V over T plus V equals NV minus V MV, wait, hold on, N on 2V, N on 2V plus V. So all the V's cancel out, and that just equals N on 2 minus 1 and N on 2 plus 1. So for N equals to 2, then we get W equals 0. For N equals to 4, then 2 minus 1, 2 plus 1, so you end up with W equals a third. So it acts like radiation. N equals 3, you get something that's weird in between the radiation and matter, where N equals a fifth. So you can do this for a general N. So from this perspective, it should say that the phi min doesn't matter, but then why does it matter here? Okay, let's start from the beginning. So we have this equation like this, and V is that, and we end up with this solution. I think that'll be fine. M squared. Is it M squared here? Yeah. Looks exactly the same. So kinetic energy stays the same because the derivative would drop out the constant. Potential energy will be slightly different. Oh, weird. Sorry, I actually honestly don't know. Oh, yeah, Felix got the answer. Oh yeah, true. Yeah. There we go. Okay, okay. Good point, good point. So V is half m squared phi minus phi min squared. Okay, let's see if that works. Half m squared, what's phi again? I already forgot. Phi naught cos mt plus some constant m squared. And then minus, okay, I should put this constant in actually, that'll make this easier. So what was the constant again? It was that m squared phi min, okay. Okay, so the constant is actually just phi minimum. So then this is just phi minimum. Okay, so yeah, okay, so this is plus phi minimum and then minus phi minimum squared. Okay, yeah, Felix solved it. Here we go. So then these two disappear and then you end up with just the same. Whew. Close. Okay, yeah, so yeah, overall, it doesn't really matter what the minimum is because this cancels it out. All right, all good. Then that is all. Any other questions? No? If not, then yeah, feel free to ask any other questions from earlier weeks as well. If not, then I'll I don't know, see you guys somewhere else, and good luck with the exams and studies. And hopefully Mikhail's questions are not as hard as his tutorials. All right. Miss Sam, yeah, hopefully the final exam is just as nice as Miss Sam. You're welcome, guys. See you guys.